Graph neural networks are information processing architectures that rely on local information, have a distributed implementation, and scale. Collaborative intelligent systems consist of a team of autonomous agents that need to collaborate to solve a global task. These agents have the ability to make the autonomous decisions based on communications with neighbors and their own perceptions. But these actions need to be conducive to solve a global task, even though they are based only on local information. In this segment, we will use graph neural networks to learn decentralized controllers that achieve the global objective acting only on local observations. As an illustrative example, consider the following robot swarm, where we want the team to coordinate on their individual velocities without colliding with each other. This is a very easy problem to solve if we allow for centralized coordination. We just set each individual robot to fly with the average velocity of the team. But it is very difficult if we do not allow for centralized coordination. And it is very difficult to solve precisely because of the information structure of distributed systems. This partial information structure is what makes designing behaviors quite challenging. The partial information structure implies that node I has access to its own local information at time t, and the information of its one-hop neighbors at time t-1, and the information of its two-hop neighbors at time t-2, and so on. Now, while optimal centralized actions pi star can oftentimes be easily computed, they require access to all states x of t. That is, x of t has the value of the state for all agents, and pi star depends on this value, thus requiring knowledge of the state of the entire team at the same time. I would like to clarify that we will be using the terms policy, action, and controller interchangeably, all denoted by pi. In all cases, it represents the decision, the actuation, the agent has to make. What we actually want is to take distributed actions that only depend on the local information history. This information history, or partial information structure, is the collection of past values available at each node. That is, the information history at node I at time t, calligraphic x sub I of t, is the collection of neighboring states with increasingly delayed values, as we just showed in the previous slide. As it happens, optimal distributed actions pi star constructed based only on the information history are famously difficult to find. As a matter of fact, Pitzenhausen showed as far back as 1968 that even for a simple linear problem, the optimal distributed controller was actually nonlinear. So, what do we do when optimal solutions are out of reach? We resort to heuristics, in particular to data-driven heuristics. The data-driven heuristic choice resides in adopting a learning architecture that naturally processes distributed partial information. That is, we parameterize the distributed action pi that relies on the information history x sub I of t by means of a graph neural network. Since GNNs are naturally local and distributed information processing architectures, we are certain that whatever GNN we pick will result in a distributed action pi that respects the partial information structure, the information history. By choosing to use GNNs as a data-driven heuristic, we have constrained the space of all possible distributed actions to be the space of all GNNs. To pick an adequate GNN, that is, to train the GNN policy pi, we use imitation learning as a means of finding the appropriate set of filter parameters h. Imitation learning relies on the availability of an optimal policy pi star that can be computed during training time. This optimal policy can be a centralized one since it is only required at training time. The objective is then to find the parameters h of the GNN that makes the decentralized GNN-based action pi as closest as possible to the optimal centralized policy pi star. The loss function L is typically any function that compares two actions, for example, the MSE loss. Note that the expectation is taken with respect to the optimal policy pi star. This means, of course, that we need to have access to the decentralized controller and the resulting centralized trajectory that stems from applying it. we emphasize that decentralized policy and the resulting optimal trajectory is required at training time, but not at test time, when the GNN has already been trained. That is, when the best parameters H that make the GNN imitate the optimal policy have been found. So, we know that GNNs are definitely a good choice to parameterize decentralized policies precisely because GNNs are based on neighboring information and have a distributed implementation, naturally respecting the partial information structure imposed by distributed systems. But even more so, the properties of permutation equivariance and stability that we proved GNNs have actually play a key role for the success of decentralized GNN-based policies. Recall that permutation equivariance means that if two agents observe the same input, their k-hop neighbors observe the same inputs, and the local neighborhood structures of the graph are the same, then the output of the control policy is the same at both nodes. In practice, this implies that the only thing about which each agent cares is the information arriving from the neighboring agents and does not need to know the topology of the entire graph. Stability, on the other hand, means that if graphs are similar, then the GNN outputs will be similar. That is, the graph topology can change slightly without altering significantly the actions GNN-based controllers will take. In essence, agents with similar neighborhood and similar neighboring information will decide upon similar actions. Both of these properties are a necessity for offline training. If we want to train offline and execute online, we can't assume the graph is the same. We want to train offline on a graph like this and execute online on a graph like this. In other words, not only the graph signal, that is, the agent states, will be different between training and testing time as is usually expected, but also the graph supports, the inherent structure of data, will be different, at least slightly different, from training to testing. That is, both the graph signals, the agent states, as well as the signal structure, the graph supports, that we will face at testing time won't have been observed at training time. This, of course, means that the fundamental properties GNNs exhibit makes them perfect parameterizations of decentralized policies that respect the partial information structure of distributed systems. GNN's use of graph convolutions means that we learn parameters H that can be run on any S. That is, what we are learning are the scalar filter taps HK of the GNN, and we can then go ahead and use these filter taps on any shift operator S irrespective of shape or size. We just evaluate the polynomial of the graph convolution on a different shift operator matrix, but with the same learned filter taps. Permutation equivariance means that GNNs exploit symmetries and reuse data. As we have discussed, GNNs learn based on local data and are influenced by the neighborhood topologies. So, all parts of a graph with the same local neighborhood topology are able to learn from seeing data in only one of these parts. Thus, permutation equivariance is key for generalizing from offline trajectories to online ones. And stability means that similar graphs will yield similar outputs. This is undoubtedly a key property for learning in distributed systems. Since the graph support depends on the actions taken, the graph support is changing constantly with time, so we need controllers that are robust to these changes in the graph. So in essence, GNNs are not only an obvious choice due to their ability to process the partial information structure imposed by distributed collaborative intelligent systems, but also because their properties of permutation equivariance and stability allows for offline training that carries over to online execution.